I'm going to discuss further methods for calculating limits, and in particular by using a collection of theorems about limits. The first theorem is squeeze theorem, and the next one is the limit of sine x over x as x goes to 0. Now, I'm going to derive what that is and do it, basically by a proof, but you don't need to know that proof, so if you're not interested, you can skip it. I just provide it because I hate telling somebody to memorize something when an explanation is available and not that hard. So half of this video is devoted to squeeze theorem, which it comes up in most calculus classes. The other half of this video is a proof of the value of this, which if you want, you can skip. So to start with squeeze theorem, the idea behind squeeze theorem is that if you have any given function, and suppose it looks like that, and we're interested in the limit of this function at some particular point, and we, for whatever reason, can't calculate it easily, but we do know that there is some function which is always greater than it, and there is some other function which is always less than it. If these two functions, the red and the green function, go to the same point, then the function that's squeezed in between it, the one we actually care about, must go to the same point. That's the idea. So, for instance, one of the main canonical examples where this comes up is with x squared sine 1 over x. So this is the thing that we want to know the limit of. And why is this hard? Well, as x goes to 0, sine 1 over x just oscillates wildly between -1 and 1. After all, 1 over x is going to infinity as x goes to 0, and as 1 over x goes to infinity, we're plugging in a ton of values into sine, and so it's just oscillating wildly. But then we have it multiplied by x squared, and that might drag this value down to 0, even though sine is oscillating wildly. Or something else might happen, we don't know. And the point is, you could make a guess, but it's really only going to be a guess. We want a rigorous demonstration of what this value is. So, for, the way that we use squeeze theorem is to remark that sine of 1 over x is always between -1 and 1. And so if we replace it with its lower bound -1, we get a lower bound function, right? This will always be less than or equal to x squared sine 1 over x. And if we replace sine 1 over x with +1, then that becomes an upper bound function. And now we have it squeezed between some two functions. This goes to 0 as x goes to 0. This also goes to 0. And therefore, by squeeze theorem, the limit as x goes to 0 of x squared sine 1 over x is equal to 0. So, so in the illustration here, this would be like x squared, right? The red function would be like x squared, an upper bound function. The green one is -x squared, and the blue one is the one that we actually care about. It is this x squared sine 1 over x. And there is the use of squeeze theorem. Now, for the rest of the video, I'm going to provide a proof that the limit as x goes to 0 of sine x over x is equal to 1, which is something you might not have expected. The top goes to 0, the bottom also goes to 0. So what does this do? Well, if the top went to some other number like 1, then we'd say it just goes to infinity. But since they both go to 0, it's really hard. There's no universal rule for what happens there. So we have to come up with some other way of deriving the value. Now, I've done a demonstration in GeoGebra because this is so geometric. So I've noticed that we are trying to talk about sine x over x and therefore relate an angle to its sine measure. So I draw a unit circle. That's going to be important. It is a unit circle of radius 1. And I have marked off an angle, and the green segment is the same as the sine of that angle. Now, what is also kind of interesting is that because it is a unit circle, this arc length in red is also equal to x, the angle. So the green segment is the sine of the angle. The red segment is the same in measure as the angle itself, right? Because this is due to S equals r theta from high school geometry, where r in this case is equal to 1. So this just is the same as the angle measure. And so this justifies saying that sine x is less than or equal to x, because you can see that this arc length has to be longer than the green segment. Now, I also want to convince you that x is less than or equal to tan x, and tan x in this problem is the length of the segment from E to F. How do I know? Well, if I look at this triangle AEF, I know that tangent is opposite over adjacent, and adjacent is equal to 1 because it's a unit circle. So the tangent of the angle is E to F. And I suggest that it is pretty clear that this E to F is longer than the angle, or the arc. Now, I could give a more rigorous justification than that, but it'll take some time, and I don't want to get too distracted, so I'll leave that to anybody who wants to prove it to themselves. But somewhat visibly, it is clear that the arc is smaller than segment EF, and therefore we have this inequation. Now I can manipulate it and apply squeeze theorem, right? I divide by sine throughout. I take the reciprocal, and you should sort of understand that when you take the reciprocal in an equation, everything gets flipped around. And again, that's a proof that I'll leave to you, the viewer, unless maybe somebody asks me for it. But I'm going to take that as given, that when you take the reciprocal, you flip it around. And now we apply squeeze theorem. As x goes to 0 on the left, this goes to 1. This just always stays at 1. So this is squeezed in between and goes to 1 as x goes to 0.